on here. And make sure I also share my screen with you guys. And so if you go to today's weekly lesson, the very first link is 3A notes, and that is the understanding modeling notes here. So the very first question I have for you there, when I say the word model, what does that mean to you? So let's raise your hand, let's talk, let's discuss. You know, take a couple quick seconds, talk to each other. I say the word model, what does that mean to you? Especially as engineers, that might mean something a little bit different for you guys. Okay. What else?
A way of presenting information.
Okay. About like a fashion model, Mr. Can, be on the cover of magazines, right? Oh yeah, you want to see that, don't you? You want to see me strutting my stuff, right? You know, fashion model, there you go. There's a lot of different models out there. But even a fashion model, they still have that generic definition that we think of a model, that they're kind of showing off clothes and things like that. They're modeling the clothes. They're showing you what it could be like. And so we have models up here, airplane model, car models. A lot of you probably play with models when you're a car or when you're a little kid. I mean, Hot Wheel, which is one over there, that's a model of a car. And most Hot Wheels are actually pretty accurate when it comes to being a 1/64th model of a car. They do a pretty good job at being a car model. We have, you know, a fashion model. We have models in art class where we model people, things. You probably made models in science classes. You got different types of models up here, model of the solar system. So a model is basically a representation in order to try to visualize something that's really complicated or hard to visualize. So for example, when you try to buy clothes, and you're like, I don't know what this is going to look like on me. We hire a fashion model to put on the clothes and show you, hey, this dress might look like this on you. Now, obviously, you have to be mindful of that. As you know, when looking through the magazines, is the dress that looks like on that person can look exactly the same on you. Okay, or that outfit, that shirt, you know, that jacket, whatever it is. You know, but they're trying to show you something that's hard to represent. You don't know what it's going to look like on you until you look at somebody else wearing it. So the same thing with models in science class is representation of something in the real world, especially something that's difficult to see or understand. Okay. Now here's the thing about models, and this little blue box down here, you might not be able to see it. Is that all models are wrong. That's the whole point of a model. All models are wrong, but some models can be useful. A model is not perfect. That's the whole point of a model. When you have a model car, it's not going to drive down the road with people in it. Right? That's the whole point of a model car. When I have a model solar system, I don't care how perfect you make that model solar system, it's not the real solar system. You can't make the real solar system, right? So all models are incorrect, but that doesn't mean that they can't be useful in order to, you know, understand a complicated idea. I like this picture here. This is the model of what people thought that the universe looked like back in 1600, with the Earth being at the center of the solar system of the universe back then, what they put it as. Okay? But again, using that information, scientists can do experiments, they can gather data and gather information, but then make predictions. Based on this model, will this happen? And sure enough, when you make a model with the Earth being at the center of the universe or center of the solar system, and you do experiments and you collect data, it doesn't work. Okay, when you make those models, it doesn't work. Okay, the solar eclipses don't work. The revolution of other planets don't work. So what happens to the stars throughout the season? It doesn't work when you make a model with the Earth at the center of the solar system. Whereas if you make a model with the sun at the solar system and Earth going around it, and the moon going around the Earth, then the data, the information, the prediction that people have, it starts to work. Okay? And it wasn't really until we actually sent rockets to outer space to prove this idea. Okay? So we actually get out there and see that Earth is not the center. But again, using models, we can make predictions. We can test to see if they're right. Okay? And again, this was Copernicus' idea back in the 1500s that the sun was the center of the universe, not the Earth. And again, it took a little bit of science, a little bit of modeling to figure this out. You have to also remember that they weren't really doing experiments back then. They weren't really trying to figure out the stuff. They just had an idea and they went with it. Not really science with it. So, assessing the accuracy of models. But all models are wrong. We just said that. Okay. One of the things that we do with modeling is what we call hindcast or forecasting. Probably heard that before. Forecasting the weather. When you forecast the weather, it means you're looking forward. You're predicting what the weather will be like. And as a weatherman in the future, if you want to, that job, it's very, very difficult to predict the future with weather. It's extremely difficult. Weathermen are oftentimes wrong. We say that kind of stuff often. We laugh at weathermen, that kind of stuff. But it's extremely difficult to predict the future of weather. And that makes sense. Okay, hard to predict the future. What's it going to be like? Hindcast, we use models to look and see what was it like back in the past. Yes, we can do that. We can make models of what was it like when the dinosaurs were alive. We don't know. We weren't there. But we can make models, and then we can run tests, we can run experiments. That if the Earth was like this, what other things would have happened? Okay? And so we can actually use models to look back in the past as well. Again, we don't know for a fact what it was like back then because we weren't back there. Okay, but again, we can use these. The main, most important thing that we have to make sure that we think about, especially as scientists and engineers, does our model fit the observation that we're making? But again, all models are wrong. But does the model fit the expectation? And then if it doesn't, we need to fix those models. We need to make them better. Okay? And that's what science is all about. We're trying to predict the future on weather or whatever it is. Our models need to get better and better and better and better, learning from the mistakes that we make along the way with our models. Okay. So the way we do that is we assess our model, we test our model based on the data that we do have, that we did gather. So I'm trying to predict the weather for tomorrow. Well, guess what I'm going to do tomorrow? I'm going to record the data. I'm going to gather the information. Was I right? Was I wrong? What was wrong with my model? How can I make it better next time? And ultimately, that's the real job of a weatherman. The job of a weatherman is not to get up in front of a board and have a cameraman and go, hey, look, this is what's going to happen. That's not the job of a weatherman. The job of the weatherman is to say, hey, what did I say yesterday? Why was it right? Why was it wrong? So that tomorrow I can make a better prediction for my people that I'm trying to predict the weather for. And I use weather because it's a common model that we use, and it's one that we're going to use today as well. If we have information about the past, fossil record, ice cores, whatever, okay, does our model fit the information we find about the past? And again, if it doesn't, we need to fix that. If we find data that the dinosaurs all lived in Antarctica and on icebergs, well, we need to fix what we think the Jurassic Park looked like, right? Jurassic Park should be a snow, ski resort, not a jungle, if we find that data. Okay. And then, of course, test it against other models and figure out who is more correct, who is better when we're making these models. Okay. So again, we said that all models are incorrect, but it doesn't mean that you can't use them to make predictions and make observations. There will always be uncertainty in science, and that's the awesome part about science. There's always uncertainty. There's always going to be things that we can do better and learn from. Okay? So, how we use the term of uncertainty is important, and how scientists use that term is important, because again, it doesn't mean it's wrong. You will never hear a scientist say, I'm 100% right about anything. But you will often hear scientists say, I'm 95% sure, 99% sure. Okay? And that's not them just making up a number. They actually can literally do testing to prove that they are 95% certain. They're 99% certain. And as you can imagine, it's very difficult to run a test and say, I'm going to be 99% certain that this is the outcome. Okay? Because you have to factor in all the variables there. Okay? There are lots of variables that interact with each other, especially in a super complex model. The more complex they are, the more uncertainty is going to be. And that's important when we talk about climate change going into the future. There's a lot of uncertainty about the future because tomorrow we could all change, we can all say we're going to fix it tomorrow. Or tomorrow we could all say we're going to make it worse. There's a lot of uncertainty involved when it comes to trying to predict the future with climate change and things like that. And so we are especially going to be focusing on weather, ecosystem, and climate models for this. So how scientists deal with uncertainty is by testing their models and using statistics. That's what we were just saying there. Okay, they run the model, they run the experiment multiple times to say, what might it be like 20 years from now? And if the model keeps putting out 20 years from now, this is going to happen. 20 years from now, this is going to happen. Same thing, same thing, same thing, same thing. Scientists will start getting an idea that, well, that might be what happens in the future. Okay. So for example, and you're going to see some of these, well, you're going to see a lot of these maps today. With hurricane modeling, you've probably seen a lot of these before, where the weathermen, the people are trying to track where is the hurricane going to hit? Where is it going to land? And that's super important, if you can imagine, right? If you don't know where the hurricane's going to land, you're going to have people that get killed by the hurricane. So this is a super, super important idea for weathermen. Try to predict where is the hurricane going to land. Do we need to get people out of there? How strong is the hurricane going to be? Right? These are life and death decisions that these people are making. But there is always going to be a degree of uncertainty. They don't know exactly what's going to happen. And so what a governor might do is say, this looks like it's going to hit, to be honest with you, it looks like it's going to hit D.C. and New York, that's what it looks like. You know, the governor, mayor, D.C. might say, hey, we need to evacuate D.C., we need to evacuate New York. Obviously, I can make predictions for what's going to happen 1 second from now. 1 second from now, Lee's going to take a drink. Oh, he's taking a drink. Right? I can make observations and I can make predictions. 1 second from now, you're all going to be all tired and sleepy, tired of listening to Mr. Kane. But I can make predictions for 1 second using observation and data. Can I make predictions what's going to happen 4 or 5 days into the future? That's where uncertainty comes to happen. Okay? And so you see oftentimes, especially on a hurricane model, it's a cone. I'm very sure what's going to happen today, this minute, but I'm less certain what's going to happen the further into the future I go. But then eventually the cone gets so big that who knows what happens a month later, a year later, after that hurricane, right? And so again, this is a pretty important idea of using models to make predictions. Okay? So the idea here, this is another one, is, so we have two different models here. We have a pink and a blue model. Does the model match up with the observation? Okay. And we can make multiple different types of models. Does the model match the observation? Does the observation match the model? And so we look at climate change. Based on all the natural data, this is what should be happening with climate change in the last 100 years, the blue line. This is what should be happening, take out humans. In the last 100 years, climate sure went up a little bit in the 1950s, and we got smart about climate in 1950s, 1960s, 1970s. We started gathering data like, hey, we need to knock off, certain things, we need to knock off certain chemical production. Take away the human impact, climate change should be that blue line. Well, if I make another model, I said, okay, let's take a natural and human aspect to get the pink line. Pink line suggests that, well, if humans cause the natural changes, the temperature's going to go up. We're not doing anything to make temperature go down. Right? So there is no model that says temperature goes downward. Okay? And so take into account human, you say temperature's going to go up, that pink line. And then the black line is the observation. What are we observing in the last 100 years? And so if I was going to bet money on which model is more accurate, I'd say, hey, I'm going to bet the blue line or the pink line. Every one of you here would bet the pink line, right? For 2010, 2020, 2030. If you had to bet money, would you pick the pink or the blue for tomorrow? You would, based on observation, based on trend, you would bet the pink line, right? Now again, does that mean it's going to happen? No, we don't know. It's the future. But if I had to make a prediction, if I had to put money on it, based on this graph alone, I would bet whatever the pink line said, not whatever the blue line says. And that's essentially all scientists are doing. They're making models, and then they're matching observation with that model. And then as you get more data, more information, you make your models better and better and better. Because again, you might be wrong. That's fine, fix the model. You might be wrong tomorrow. That's fine, fix the model. You might be wrong next week. Fix the model. And as you become more and more wrong, your model becomes more and more better. Because you're learning from that data, you're learning from that information. And that, again, that's the cool part about science. It's fluid. It's always changing. Right? To be honest with you, our models about climate change are wrong. They tend to be too low. They tend to be too conservative. You know, the data we're collecting is worse than scientists think. The ice is melting faster than we thought. The temperature is rising worse, quicker than we thought. But again, we're changing the model. And that's why we say stuff like, well, there's probably not going to be any glaciers left in the next 20 years. And now they're saying, well, there's probably not going to be any glaciers left in the next 15 years. Again, that's my model. My model is predicting that glaciers, and that's what they are saying, by the way. They're saying that the glaciers and mountains probably aren't going to be around much longer. So all the people that depend on water coming from glaciers and ice are going to have difficulty getting that water. Okay. All right, so for our state today and Wednesday, and I'm not going to talk a lot on Wednesday, we're going to look at models, and the most important thing you need to kind of understand for today is the idea of a high and a low model. That's all you really need to understand, high and low. The other thing you might want to make sure you understand is these names. These names, Hadley, that's just a group of scientists that made a model. And again, they're just not pulling it out of their butt saying, hey, here's the model. They're using data, they're using information to make predictions on the future. So all the names you get in front, it's just a group of scientists led by a Dr. Haley or whatever, okay? Or it's NASA, or it's, you know, a city or a college, okay? It's somebody's model, Hadley. But the most important thing you need to understand, high versus low. A high model, again, remember that degree of uncertainty. A high model is what's the worst case scenario, the highest amount of change. The low model is what's probably the least case scenario, where's probably the lower trend that might happen. If you look at these two pictures, especially for Kentucky, you will see that Kentucky is going to change. The question is it going to change in a high way, or is it going to change in a low way, low emission? So today, currently in Kentucky, these are temperatures, by the way. I know you can't really see it very well, but these are temperatures. The lower temperature is the tan color. The medium temperature is the greenish color. And then yellow is a little bit hotter. but then you get a little bit pinker and redder and purpler. Okay, so you get a lot of changes in temperature. So today in Kentucky, we're tan and green. So to have the low model suggests, and I don't know exactly when, I don't have a lot of information here. I don't know if it's 10 years into the future, your model's in there, they have information. But the Hadley model suggests in the future, Kentucky's probably going to be a little bit of the light pink, maybe even a little bit of the yellow for the lowest possible change. And so if you look at the graph, that suggests a temperature change of about, again, I have a hard time seeing that on there, but, you know, it's not one box different, it's 3 boxes different. So if you look at that trend on there, that Kentucky's going to change a little bit. So for the low model. If you look at the high model, Hadley Research Group said, Kentucky could be neon green or purple or red if on a worst case scenario. So worst case scenario, we're way over here, we're 6 or 7 boxes increase. Again, I have a hard time reading those numbers, they're really small, but you can zoom in on yours. Okay. So for the least case scenario, they're saying Kentucky's going to increase by 3 boxes, 3 colors. The worst case, the high scenario, Kentucky changing by 6 or 7 boxes. And again, I think that's a couple degree difference, like probably 2 or 3 degrees difference. So lowest case scenario, we're changing by 6 degrees. Worst case scenario, we're going to change by 10 or 15 degrees average. So what do you think is most likely to happen? Do you think we're going to be extremely low, extremely high? We're probably going to be somewhere in that cone, right? Like the hurricane. We're probably going to be somewhere in that cone of the lowest case scenario and the worst case scenario, somewhere in there. And maybe it's worse than we think. And I will say this, these models you're going to look at today are kind of old. They're about 6 or 7 years old now. So we can look at more modern data and take a stab at what it's going to look like. But these models are a little old for us. So again, this is a cone. The least case scenario versus the highest case scenario will probably be somewhere in there. We might get lucky. We might be lower than we expect. Might get unlucky. We might be higher than we expect. So today you're going to look at temperature. You're going to look at rain, I think. And precipitation. I forget what else you're going to look at today. I think it's mainly temperature and precipitation for today's activity. Next, on Wednesday, we're going to look at plant life and animal life. Next on Wednesday. So if you open up today's activity, I think that's it for me today. Yep, that's the last slide. If you open up today's activity, it's going to show you some actual models. Atlas of Exchange A. You need to fill in the yellow boxes. This is a Google slide, so when you go to upload it or submit it, you need to go to your Google Drive and find it. So make a copy of this. And, all right, so here, let's make more sense. So it was temperature degrees, but boy, that was a 6 degree temperature, the first graph. The second graph was a 15 degree difference. That was more than I thought. Okay, so that is temperature, and that's a little bit easier to see now that we can actually zoom in on it. Okay. All right. There are a couple questions for you to answer about Fahrenheit versus Celsius. That's important there. Okay. All right. So there are a couple questions here. Based on the high estimate, what is supposed to happen in Kentucky in our area? Okay. And then focusing a little bit on Fahrenheit as well. If you don't know the change in Fahrenheit to Celsius, it's a 5/9 fraction change plus 32. You can Google it. Change Celsius to Fahrenheit. It's super easy. It is kind of a weird formula, but it's not too complicated. All right. And then, so again, this graph here, we have a different group of scientists. PCM, probably an acronym. Scientist, Dr. P, Dr. C, Dr. M, or a location or a city or something like that. Probably a different group of scientists. This is their low model versus Hadley's model of high. And again, there are different scientists making different models here, but ultimately, I hope by the end of this, you'll see that scientists are predicting that there will be a change, unfortunately, so, and a change in our climate. Okay, that's your work for today. Not a lot. Just because the boxes are big doesn't mean you got to write a paragraph or anything. Just answer the question. You know, doesn't mean you have to write a whole bunch. There is an extra slip at the end about do all scientists agree, and then they agree that something will happen. Okay, so we got about 10, 11 minutes to work on there. It might be a little bit of homework tonight. You can work on it tomorrow. Tuesday, Thursdays, we are going to kind of start transitioning out of YLPs and get back into a little bit of remediation as the school year ends. So you guys should be pretty much done with YLP as far as I'm concerned, the testing and the data collection. Make sure you're putting that on your YLP. So in that little presentation you're making, we should see those pie charts, we should see those bar charts, the 50 random choices. All right. Let me know if you have any questions. All right, what do you do? Stop the video.